You are on a fabrication job. Steel plates. Butt welds. A purchase order to raise by tomorrow morning. The question every engineer and supervisor dreads: how many kilograms of electrode or wire do I actually need? Order too little, you'll stop the job midway. Order too much, you've tied up budget and storage on material that just sits there. In this video, I'll show you exactly how to calculate weld consumable for a single V-groove butt weld joint, the most common joint type in structural and pressure vessel fabrication. We'll break down the groove geometry, calculate the area step by step, find the weld volume, and convert it into actual kilograms of electrode for any welding process. All with one real-worked example. Stay with me, this is simpler than it looks. Before we get into the numbers, let's be clear on why this calculation matters in the real world. First, cost control. When you know exactly how much consumable you need, you buy exactly that amount, no over-purchasing. Second, no last-minute panics. Running out of electrodes on a critical weld can halt an entire fabrication line. Third, vendor management. If you are supplying consumables to a subcontractor, you give them precisely what they need. And here's the one most people overlook: wastage monitoring. When you know the theoretical consumption, and you compare it to what was actually used, that gap tells you everything about your welding efficiency, your stub losses, your spatter levels. It's not just a purchasing tool. It's a quality and efficiency tool. Now let's calculate. Let's define our joint. We have a single V-groove butt weld with the following dimensions, as specified on the engineering drawing. Plate thickness T equals 15 mm. Bevel angle equals 35 degrees on each side. Root gap G equals 3 mm. Reinforcement height R equals 3 mm. Total weld length equals 1000 mm, that's 1 meter. And our material density, carbon steel, is 7.85 grams per cubic centimeter. Now here's the key insight with any groove calculation: don't try to calculate the entire cross-section as one complex shape. Instead, break it down into its simplest components. For this V-groove, we have 4 parts: 2 triangles forming the bevel, a rectangle at the root, and a rectangle at the cap reinforcement. Calculate each area individually, add them together, and you have your total groove cross-section. Simple geometry. Let's start with part, the root rectangle. This is the simplest shape. It's a rectangle with a width equal to the root gap, 3 mm, and a height equal to the plate thickness, 15 mm. Area of part equals length times breadth equals 15 times 3 equals 45 square millimeters. Parts N are the bevel triangles, one on each side of the groove. Because the bevel angle is equal on both sides, their areas are identical. So we calculate one and double it. For a triangle, area equals half times base times height. The height is the plate thickness, 15 mm. The base we calculate using trigonometry, it equals tangent of 35 degrees, multiplied by the plate thickness. Tangent of 35 degrees is 0.7002. So the base equals 0.7002 times 15 equals 10.503 millimeters. Area of part 1 equals 0.1 times 10.503 times 15 equals 78.77 square millimeters. And part is the same, 78.77 square millimeters. A quick note on the bevel angle. The 35 degrees here is the angle from the vertical, the angle of each individual bevel. So the total included angle of the groove is 70 degrees. Always check your drawing carefully. Some drawings show the included angle, some show the bevel angle. Know which one you have. Part 4 is the reinforcement, the weld cap that sits above the plate surface. This is approximated as a rectangle. The height of the reinforcement is given as 3 mm. The width of the cap spans the full top of the groove. Width equals 2 times tangent 35 degrees times plate thickness plus root gap. Width equals 2 times 10.503 plus 3 equals 24.006 millimeters. Area of part 4 equals 24.006 times 3 equals 72.02 square millimeters. Now we add all 4 areas together. Total area equals 45 plus 78.77 plus 78.77 plus 72.02 equals 274.56 square millimeters. That is the cross-sectional area of the weld groove, including the root gap and the reinforcement cap. Step 3 is straightforward. Volume equals area multiplied by length. Volume equals 274.56 square millimeters times 1000 mm equals 274,560 cubic millimeters. Now we need to convert that to cubic centimeters, because our density is in grams per cubic centimeter. To convert cubic millimeters to cubic centimeters, divide by 1000. So volume equals 274.56 cubic centimeters. Keep an eye on your units throughout this calculation, it's the most common mistake. Millimeters squared times millimeters gives cubic millimeters. Then divide by 1000 to get cubic centimeters. That's the unit that works with our steel density value. Step 4. Multiply volume by density to get the weight of weld metal deposit. Weight equals 274.56 cubic centimeters times 7.85 grams equals 2155.3 grams, which is 2.155 kilograms. Important. This is the weight of weld metal that needs to be deposited into the joint. It is not the weight of electrode you need to purchase. That comes in the next step. This is where people make the big mistake. 2.155 kilograms is what ends up in the joint. But because not all of your electrode becomes weld metal due to spatter, slag, stub losses, you need more electrode than this. How much more depends entirely on which welding process you are using. And that's where deposition efficiency comes in. Deposition efficiency reference table. To find actual electrode required, divide the weld deposit weight by the deposition efficiency. For SMAW at 62.5% efficiency, 2.155 divided by 0.625 equals approximately 3.45 kilograms of electrode. For GMAW at 97%, 2.155 divided by 0.97 equals 2.22 kilograms of wire. For GTAW at 96.5%, 2.155 divided by 0.965 equals 2.23 kilograms. And SOR at 99%, just 2.18 kilograms. Look at the difference between SMAW and GMAW in our example. SMAW needs 3.45 kilograms of electrode for this 1 meter of weld. GMAW needs only 2.22 kilograms of wire. That's a 35% difference in consumable cost, just from process selection. Now multiply that over a fabrication job with 500 meters of butt welds. Suddenly that difference is not just a number on paper, it's a very significant line item on your project budget. This is why prefabrication consumable calculation is a critical engineering task, not just an admin exercise. One final practical point, always add a contingency buffer when placing your purchase order. A standard allowance of 10 to 15% above the calculated quantity accounts for setup welds, trial runs, wastage, and any re-welds required. So for our SMAW example of 3.45 kilograms per meter of weld, add 15% contingency and your order quantity becomes 3.97 kilograms per meter, round it up to 4 kilograms for simplicity. Let's recap the 5 steps for single V-groove consumable calculation. Step 1. Collect your groove parameters, thickness, bevel angle, root gap, reinforcement, weld length. Step 2. Break the groove cross-section into simple geometric shapes, rectangles and triangles. Step 3. Calculate each area and sum them to get total groove area. Step 4. Multiply by weld length to get volume, convert to cubic centimeters. Step 5. Multiply by steel density 7.85 to get weld deposit weight, then divide by deposition efficiency to get actual electrode or wire required. The method we just walked through applies to any V-groove butt weld, pipes, plates, pressure vessels. Change the inputs, the formula stays the same. If you want the Excel calculator to do this automatically for single V, branch joints, and fillet welds, download it free from weldfabworld.com. Link is in the description below. If this video helped you, please hit the like button, subscribe for more practical welding engineering content, and leave a comment with your questions. I reply to everyone. Until next time, keep welding, keep calculating.